Let's take a look at another example. Here we've just changed the problem a little bit. We still have initial conditions. We can turn this into our characteristic equation very easily. And we end up with r squared minus r plus a quarter equals 0. That turns out that factors perfectly too into r minus a half squared, and so r equals 1/2. We only got one solution, so the first fundamental solution is going to be e to the 2t. And we can, because we only got one of them, multiply by t to get the second fundamental solution. Plug in the initial condition, so plug in a 0 for t. That takes that whole term out because 0 is going to be t. That'll kill that whole right term. And if we plug in 0 over here, you just get c1. And you also need to differentiate the solution. And when you do that and use the product rule here, you're going to get this expression. Solve it using any linear algebra method you like, including substitution, and we have our two constants. So here is the final solution. So the nice thing is, even though this method looked bad at the beginning, it really turned out pretty well, and we end up having a fairly simple system. Okay, and I think really not too much more to say. Oh, I'm sorry. So what they've said here is, now suppose we change the slope. If you change the slope initially, in other words, if you change the initial velocity of the system, it really has quite an impact on the result, and it causes the solution to go the other way. So again, this is one of those bifurcation things that a small change in one of the initial conditions will cause a completely different direction of the solution. Okay, one more thing to share with you. It's going to seem like a complete change of topic, but it is very much related to the method that we just used, because we're going to reuse the same method. And that is to say, well, what if we only had one solution to the differential equation for whatever reason? So now we're going outside of the realm of constant coefficients and assume that we have variable coefficients, variable with respect to time. And let's suppose we were able to find a y1, just like we did in the case where b squared minus 4ac was 0. This time for different reasons, because it's not the same kind of problem. If we found a y1, could we apply the same approach that we did to get the second solution? Because, section 3.2, we know there's still two solutions, even to this equation here, that doesn't have constant coefficients. Well, let's give it a try. Let's take y2 equals v times y1. Use the product rule. This is getting very abstract now because I don't know what y1 is yet. I'm assuming I can get it. And I end up with this equation, and then I differentiate it again, and I get these three terms, because the middle terms combined. Well, I've got to do the same thing. I've got to take this big old ugly thing and stick it in for y double prime. I've got to take the first derivative and stick it in for y prime, and I just plug in v times y1 and stick it in for y. But I've got these other functions chasing around as well, and it's going to get a little bit more complicated. So because it gets complicated, we're going to drop all the t's to make the notation cleaner. So even when I say v double prime, I really mean v of t double prime, and the same with p and q and y1, so forth. They're all functions of t. Okay, that makes it a little more compact and a little bit easier, and so we can just go ahead and plug things in this manner. Now, there's been a little bit of collecting of terms, so there's quite a step here that I've left out, because what really happened is this entire expression got plugged in for y double prime, and it had v double primes and v primes and v's in there, and the same thing happened when I plugged in y2. I got another big old expression. Fortunately, a lot of the terms combine nicely, and we can, if you do all the simplification, you get this expression here. Okay, so you can check that on your own. That'll take a little bit of algebra, so we're not going to bother with the algebra here, and we'll just trust the fact that this is what you end up with. Now you get one more really nifty simplification that wouldn't seem obvious at first, and that is that this term, this this sort of built-in differential equation that I've got here goes away. Now, why would that go away? Well, if we look back up at the original differential equation, we are saying by definition, because this is the problem we're trying to solve, that this expression is 0. We're also saying that y1 is a solution, which means if you plug y1 double prime here and y1 prime and put it here, and you take y1 and stick it here, well, that's going to be 0 because it's a solution to this equation. Well, look what we have down here. That's exactly what we have. y1 double prime plus py1 prime plus qy1. Look, it's exactly the same thing with the solution plugged in. Therefore, this parenthetical expression must be 0. That's nice. That means all I've got left is the left-hand side is equal to 0. Well, what can we do with that? Here's our new expression. And the thing to notice is that it really is a kind of a hidden form of a first order differential equation. How can you say that? Look, there's the second derivative right there. Well, I could make a substitution. I could take a variable u and set it equal to v prime. If I did that, then u prime is v double prime. So I could put u prime over here. So effectively, this is a first order differential equation. Now let's go try that. So we're going to take a sample differential equation here. This is going to be an example. And we are going to put in our presumed solutions. We've got y2 is equal to a function times the solution. Oh, I didn't tell you over here. Somebody handily gave me the first solution, which is nice. So I have y1 equals t to the minus first. How do you know that? Check it. Okay, we're not going to do it right now. But take it and stick it in for y. Differentiate it once and stick it in for y prime. Differentiate it twice, stick it in for y double prime, and combine these terms together and you're going to get 0. So this clearly is a solution. How did you get that? Who knows? Some nice person came along and dropped it on your lap. So we're trying to find the second solution, y2, by doing this product. Okay, so these are the exact same steps we did before. We're going to take all three of these terms, put it back into the equation, and we're going to get kind of a big expression. But the same thing will happen as it did in general. In fact, I'm not sure why we have to go through all these steps, because the previous page we proved that embedded in here is the original differential equation. Well, we'll do it the hard way, and we'll stick it all in there, and we'll multiply through by these terms and combine everything, and look, it pops out into effectively a first order differential equation after I take u and substitute for v prime and u prime for v double prime. Now I really made more out of this than I had to because I knew this had to happen. I proved it on the previous page that it happens in general. So it's certainly going to happen for any specific example. This will always work. So that's kind of surprising. Now that means I can solve a first order differential equation and use it to leapfrog into the final solution, which is going to be, well, not even the final solution, it's going to be my v, and then when I get my v, I'm going to multiply it by the first solution to get y too. So it's really a daisy chain. I'm going to solve this equation to get u. I'm going to find out what v prime is, or I'm going to determine v from it through integration, and then I will determine my y2. So let's go ahead and do that. This is my nice simple first order differential equation that I want to solve. I know how to do that from chapter 2. So let's go ahead and do it. And then we end up having a nice separation of variables method that we can use. And we just need to do some integration. You're going to get a logarithm. This is taking us back almost to the first few days of class. And you end up with a solution of u equal to this expression. Now your book's being careful to use absolute values because these logarithms don't behave very nicely if u goes negative. If this were a complex function class, we might entertain that, but we're going to not do that and just require u to be positive. So after we solve this, we end up getting this expression here. We actually can give up on the absolute value because we're going to require positive t's. V prime equal to ct to the 1/2 is really easy to solve. We just do the integration and we get this expression here. You can check that, try differentiating this and see if you get the equation, if you get v prime back again. And now we're almost home free. We've got our v. Don't forget, you're not really done yet because y2 is equal to v times y1. And our y1 was t to the minus 1, or 1 over t. But that's just a simple algebraic job, and we end up getting this expression here. Okay. Now, a couple little things to note. We know that y1 was t to the minus 1. And that means, and this is going to seem a little tricky, that means that you really don't need this second portion of the solution. You know, how can I just throw things out like that? Well, if y2 is equal to the sum of these, this expression, it's kind of like I have a y3 and a y4 here. And this y4 is going to be a multiple of y1. And since we're going to be taking linear combinations of y1 and y2, this is going to just roll into y1 as being another arbitrary constant times the same function. So you don't really need it twice. So we could just really say y2 is equal to just this portion of it here, and everything else is either a constant times it, or it's another term that is a linear combination of y1. So you only pick out the portion that is linearly independent from the first solution. Let's not forget the Wronskian. Now that we have a y1 and a y2, we can do that little cross multiplication. We won't lay it all out here, but when you're done, you get 3/2 t to the minus 3/2. That, of course, has to be non-zero as long as t is greater than 0. That gives you the final solution then of y equals this linear combination of t inverse and t to the half. So check some of those things, make sure those steps really do work out to your satisfaction, and I think that that gives you another method to solve these equations. You're going to have a homework problem in which that happens. You get one solution and you have to come up with another one. Well, we did it. We got through everything we're going to say about second order differential equations that are homogeneous and have constant coefficients. We've covered all three cases. The case that produces oscillation was complex. The case that just produces exponentials, real exponential, we had two real distinct roots. And then we had this little trickier situation when there was only one root. But we solved all three of them. And you should be able to hit any differential equation with constant coefficients that you come across, because they're all solved in general. Well, next time we're going to look at a little bit harder problems as we allow non-constant coefficients and some more solutions that are associated with them. So we'll see you then.